Hello all. In this video, we're going to take a look at some of the big ideas around using agents as our organizing principle. So what do we mean by an intelligent agent? What are the different kinds of agents that we might have? And how can we have more complex systems of multiple agents or agents with different abilities that work together to solve a problem? I'm going to switch over now to showing you my notes document, and we'll kind of go through some of the ideas there. All right, so first of all, we're focusing on intelligent agents. There are other ways to try to unify artificial intelligence, which is kind of a big, broad, sprawly field. This is one that people have used for a number of years because it captures the notion that an artificial intelligence system needs to be somehow separate and contained from the environment in which it exists. And it allows us to incorporate things like machine learning where we don't always, or even something like a chess playing program. We want to somehow be able to talk about both of those things as agents, as having something in common with each other. So, intelligent agent or rational agent is a common way to describe what we are interested in when we talk about artificial intelligence. So there are key ideas here. There is that one of the key ideas is that the agent exists in an environment. So if it's a chess playing program, its environments may simply be the chess game that it's attached to. If it's a robot, it might exist in the real world. If it's a simulated bot or a chat bot or something like that, it exists in the environment where it communicates with the people or other systems around it. So each agent, intelligent agent, exists in an environment, and it goes through, in some sense, a sense, decide, act loop, which can run slowly or quickly depending on the task and the environment. But fundamentally, the agent gets some information from the environment. We characterize this as perceptions, sensory data of some kind. Can include information about itself in its own state, but it also can be just external information coming into it from its environment. It has actions that it can take that will impact that environment. In the case of a chatbot, the percept is likely to be text coming in from a user, and the action is text that the system produces. But similarly, a robot agent has sensor values and it has motors that it can control. A chess playing program has percepts around the state of the chessboard at the very least, and it has actions in terms of making moves in the chess game. So each of these fit within this notion of an intelligent agent. And then in between the senses coming in and the actions going out, the AI agent makes some decisions about what should happen. And this is where we can have some variability in terms of how much information, internal state the agent has, what kinds of tools it's using to make those decisions, and so forth. But that's sort of where we get at the guts of the agent and how it works. Okay, another key idea here is that we need to be able to state clearly and upfront, separate from the agent itself, how we can define success for the agent, how we can evaluate its behavior. Just creating an agent and observing its behavior doesn't necessarily tell us whether or not we've created a successful AI agent. So we want to be able to define what it means for that agent to succeed, and we want to focus on what's happening in the environment more than what the agent should do or how they should do it. Sometimes if we're interested in, say, modeling human behaviors with an artificial agent, we do care perhaps about how the agent does its task. But fundamentally what we want is to see an outcome in the environment that matches what we would expect from a human. So this is our framing of agents. We can be more specific when we talk about rational agents. So a rational agent, the agent selects an action that is expected to maximize its performance measure. So it's going to choose actions that it thinks will lead it to a good performance. It may be mistaken, of course, or in a certain situation, maybe it chooses the wrong move because it can't assess properly what the best move would be. But we want agents that don't just act randomly, but that are making choices that are effective. Sometimes those agents are designed by us to have that behavior. Sometimes they are developing and making those choices for themselves. Note here, we're not talking about an omniscient agent. We're talking about an agent that makes the best decision it can given the knowledge that it has. And there are definitely places where the exact rules for where this behavior comes from may be really different. So I have here a couple of references of very simple creatures in the world: dung beetles and the Sphex wasp. People have studied the behavior of these because they appear to be making very interesting and intelligent decisions, but we have sort of learned through experimentation that in some cases these decisions are hardwired in them, but they have so it's more of a result of the process of evolution that these agents have these behaviors, and they aren't actually thinking about it when they perform these behaviors. The example of the Sphex wasp is one that I think is particularly notable. It's the one I remember more clearly. So the Sphex wasp is a hunter, and it goes and it catches food, and it brings it back to its nest. But before it brings the food into its nest, it sets the food down and goes and looks in the nest to ensure that no enemy has moved in the time that it has been gone, and that it's safe to bring the food into the nest. That looks like intelligent behavior, right? It's pausing, it's checking, and then it grabs the food and moves into the nest. What researchers discovered, though, was that if they moved the food even a little bit, the wasp would perform the exact same behavior again. So if you move the food, it picks up the food, puts it right back where it was before, and then checks again to see if there's an enemy in the nest. It's a hard-coded reflex behavior that the wasp is performing, and disrupting that behavior can cause it to perform it indefinitely. As long as you want, you can keep making the poor wasp do this, and it will never realize that it's repeating itself. So we can have complex behaviors that derive from reflex agents that aren't really thinking or making decisions, but they've somehow been created or evolved to have certain behaviors that are interesting to us. That's also an interesting part of AI, is studying these kind of artificial agents. All right, this, I don't know if this is in your reading, but I like this particular breakdown. When we think about environments, it's often useful to categorize them and bear in mind these different properties that they might have that can lead them to be harder environments or easier environments for an agent to manage. So there are lots of, each of these is kind of a different dimension along which environments may differ. So the first dimension is how much of it is observable. Is the environment completely observable to the agent, or is it only partially observable? So that's sort of the difference between, say, a chess playing program where it can see the whole chessboard at all times, and maybe something that's playing poker where it doesn't know what cards the other players have. Single agent versus multi-agent. Is it the only actor in the environment, or are there multiple actors? Does it need to compete with those other actors, or can it cooperate with those other actors? That changes how you want your agent to behave. Is it a deterministic environment or a non-deterministic environment? Are there things that happen at random, or does everything happen in a deterministic way with no randomness? Like, if the agent takes an action, are we 100% guaranteed that action will happen, or is there a possibility that the action could fail and not happen at all? So a chess playing program, as an example, is deterministic. If I say move my pawn forward 2 spaces, the pawn moves. What happens after that may be a little uncertain, but the pawn does not ever fail to move. So a non-deterministic environment would be one where there's some chance that I'd ask the pawn to move and it just doesn't move. Which reminds me a little bit of games in Alice in Wonderland, if you've ever read those books. An environment could be episodic versus sequential. Is it a single isolated episode, an interaction, or is it a whole series of things that happen one right after the other? In some sense, with a chess playing program, one game of chess is an episode. It's a little, but it is a sequence of moves within that game, so it's kind of unclear which way it would go. Something like a specific chatbot that is, say, working with people and answering questions, it might be very episodic. So it interacts with one person very briefly, and then it's done, and then another person comes along. Or a program that's finding the best route, like Google Maps, it generally just makes a map and gives it to you, and that's the end of that interaction. It's not exactly something that has a sequential nature to it. Static versus dynamic. So this doesn't have to do with randomness or the effects of the agent's behavior. This is just intrinsically in the environment. Does the environment stay put, except when the agent makes changes? Or is it a dynamic environment where things could change all the time? Discrete versus continuous is another dimension. A chessboard is discrete. There are fixed positions, and we know exactly how many there are. We can have a simulated robot that lives in a grid world where it moves from one grid square to another, and it never doesn't have to deal with any other sorts of positions, versus a robot in the real world that's a dynamic environment. Everything, and it's a continuous environment. So it can be at theoretically any position in that environment, not just discrete ones. And known versus unknown to the agent. So is it a situation where the agent knows about its environment, even if it can't observe all of it? Or is it a situation where the agent does not know about its environment and needs to learn about it, maybe as it is interacting with it? There's a particular realm of AI called general game playing, where the agents are given general rules for how to approach playing board games, and then they could be dropped in a situation where they do not actually know the rules for a specific board game, and they have to sort of figure it out on the fly. So that's an example of something where maybe the situation might be unknown to the player, to the agent. All right, so there are hierarchies of agents, and in the reading that's associated with this section, there's also a section on hierarchical control, which I'm going to show you as well. So in agent hierarchy, an agent has an architecture or body, could be simulated, and a program that handles the decision part of things. We are going to focus right away on simple reflex agents. So these are agents with extremely simple internals. They do not maintain an internal state where they remember what they did last time around. They do not have complex internal deliberations around what their goals are and how best to achieve them. They don't have a model of the external world. They basically have a set of rules that allow them to respond to the sensor information, the percepts that they get in. It's often in the form of basically if this then that, or a table. You choose from the table which row matches the percepts the agent is receiving, and then the column gives you what action to take. What's interesting about simple reflex agents and why they're kind of an interesting thing to study is that when those agents interact with their environments, you often get really interesting complex behaviors like the dung beetles or the sphex wasps. You can get complex multi-agent behaviors. So the behavior of a bee swarm or an ant colony, each of the individual agents is very simple, basically a reflex agent, but when they interact with each other, marvelous things happen. We are going to study reflex agents quite a little bit. Simple agents in robotics are actually fairly common, but often that you run into a wall. There's only so complex they can be. All right, but what does a reflex agents program look like? Typically, you would have a read, decide, act loop, but it cycles very quickly because the agent isn't doing a lot of thinking. It can make decisions really quickly, and it can take those actions, and then it wants to immediately assess the result of those actions and respond to it. This is super important for the, say, the basic maneuverings of a robot in the real world. It needs to be constantly in tune with whether someone has stepped in front of it, whether the action it took is having the effect that it wants. And so you have this really rapid sense, decide, act loop. So here I have a little pseudocode that shows like what the complete program for a reflex agent might look like. Before it starts to respond to the world, you might have a setup state where you initialize it, you get anything prepared that it needs, and then it just goes into a loop that loops forever until it's time to quit. It reads the sensor values. It may process those sensor values, so converting them from one form to another. And then it has a set of if-else statements that choose, based on the process data that it has received, what action to take, and it performs that action, and that's it. And then it goes back around and does that whole cycle again. Until and unless it's time to quit, and then you need to maybe shut down the agent in whatever way is appropriate. This is very, very simple. This is what you typically have with a reflex agent. Sometimes we'll have reflex agents that have a small amount of state, so they may actually be able to remember some small number of previous inputs and the actions that were taken. This is a useful thing to do if you need to have an agent that can recognize when it's stuck. This happens in robotics a lot. You'll have, say, an environment with a corner to it, and here comes the robot, and the robot just sits there and bounces back and forth in the corner. And if you don't have any way to break that cycle, you can get the robot stuck, so it can't get out of that corner. If it can remember what it's been doing recently, it might be able to recognize that it's caught in a cycle and choose some other behavior. But oftentimes what we'll do instead is just add a little bit of randomness in to help the agent get out of situations like that. All right, now I'm going to talk about other agent types. So we talked about a hierarchy of agents. Here is a way that you can think about starting with a simple reflex agent and then adding on to it so that you get more and more complex behaviors. I'm going to take this other text away. So we can add capability. We can add a memory for previous actions. As I said before, in the readings, this is often described as the agent's belief state. What does it believe about the world? That could be simply a record of what it has done before. You could have it also using that past information in order to construct a more sophisticated view of the world, or you could have it given a more sophisticated view of the world from the very beginning. So maybe the agent is given an internal model of its external environment. So you give a robot a map, and it's allowed to use that map to figure out where it is, to figure out where it wants to go next, to reason about what's going on. That gives you a more rich set of behaviors that the agent can exhibit. It also begs the issue of what if the map doesn't match the world. There are lots of other things come up when you start to do that, but you can build agents that have internal models of the world in one form or another. You could have something that includes explicit goals and planning. So instead of the agent simply having a reflex response or an automated response that's based on the model of the world that it has some sense of its own goals, and it can choose and plan what it wants to do based on those goals. You can add reasoning about the utility of its actions. So if it has a sense of which actions have what benefit, then it can do a cost-benefit analysis and choose an action appropriately there. You can also have it explicitly representing and working with uncertainties in the environment. So if the environment has randomness to it, if its actions are uncertain, if its sensor data is uncertain, then it's often a good idea to have the AI agent explicitly acknowledge that and to plan and behave accordingly. So you could have mechanisms for representing the uncertainty, modeling the uncertainty, and similar. And you can also add learning. I will say that you can do machine learning and build a model, and then take that and have the machine learning basically turned off, and then install that model almost as an internal model of the world to get an agent that's sort of that second or third level of abstraction. When we talk about adding learning, I'm often thinking about agents that are learning on the fly, that are in the world, in their environment, experiencing it, and they are actively learning at that moment. That's not that common in AI applications out in the real world, but it is a really interesting approach, and kind of fun to work with. All right, so there's another way to think about hierarchy of agents, and that is there's some problems that are complex enough that one agent of any of these types may not be able to solve the problem completely. And what you really need is a collection of agents that are each performing a part of the problem. So I have an example here. We've been talking about playing chess. Suppose that you wanted a robot to play chess. So this is a robot agent. It's in the real world. It's needing to be doing lots of things, including observing an actual physical chessboard and interacting with it. And that adds a whole lot of layers of complexity to what the robot's task might be. And you might need multiple different agents to help it solve that problem. So you need maybe a piece of the problem is something that integrates the camera and motors to grasp and move chess pieces. So just picking up the correct piece successfully, moving it to where you want it to be, and setting it down successfully, that's a task all by itself. That's hard. It's really hard. So, especially if the agent does not have an overhead camera. But yes, being able to do that, which requires some integration of ongoing camera views and motors and sensors, that's a task in and of itself. You could have an agent whose sole task is to look at that piece of the problem. You need to be able to, if it's a robot, it needs to be able to look at the physical board and identify the state of the board. What pieces are in what locations? That is building an internal map of the world. But again, that could be an agent's sole task, is just that piece of the overall problem. You could have an agent that stores that state of the world internally, and it is able to use that and manipulate it to plan the future moves. So it's figuring out what the right moves should be. You might also have an agent, and this is going beyond our typical computer chess player, you might have an agent that's paying attention to what the other player is doing. What is the opponent doing? What is their strategy? Can you identify what kind of a player they are? Real world chess players, that's part of what you do. You figure out how someone is thinking, who is your opponent, in order to choose moves that might fool them or trick them, and help you to win the game. You might have an agent who's planning multi-step sequences of moves, not just which move should I make right now, but how is that going to play out on the longer term. You might have a player who's evaluating the costs and benefits of each move. You might want to reason about uncertainty. Chess doesn't have hidden knowledge except in terms of what the opponent is thinking. You also have the uncertainty in terms of actually moving the piece successfully, but that's a different problem. But if you're doing opponent modeling, then you have to deal with your uncertainty about what the opponent is thinking and doing. And you could certainly integrate learning into this. So all of those different aspects of an agent could be a part of a single agent that we perceive from the outside. So from the outside, we see a robot playing a robot that plays chess. Internally, it could have all of these different components that are working together. All right, so here's the key takeaway from what I've been talking about. Complex AI systems may need to integrate multiple techniques to solve complex tasks. I talked about chess playing a little bit. There's a robot example in the readings that are assigned along with this, which involves driving a car, which is clearly one that has lots of different pieces. We're going to take a look here at another example of a complex system. This is actually my own research system, and I thought it was a good chance to talk about a system that has multiple complex pieces that are each maybe being handled by separate agents. So in my research, I have a robot. It rolls around in the building. You can tell it locations that it should be trying to get to, and it needs to localize itself to see whether it's actually successfully performing the steps of the plan to get there and getting to a final goal location. So my agents have multiple, I have multiple different agents that are a piece of this. There is an odometry agent. This is very low level. It's getting information from the robot, the physical robot itself, and it also has access to some information that it can be updated from other pieces of the program as need be. But otherwise, it's basically taking the motor data and updating where it thinks the robot is in a global coordinate system. Robot-centered coordinate system that is basically an offset from wherever the robot started. So that's a very, very simple agent. It's not really doing any complex AI. It's just doing basically dead reckoning. It's calculating a new position based on the motors and the movement of the robot. There are three main components of the system that are really AI related. Here in the bottom is one called robot motion. This is actually the one that controls its moment-to-moment navigations. It's getting in sensor information about where obstacles are in the world, and it's attempting to align itself to avoid those obstacles while seeking a goal that it has in mind. So it has very, very limited information about the world. It knows where it thinks it is right now. It's told where it should be trying to get to, and it has an immediate feedback of sensor information, and otherwise it's just trying to move without banging into walls or running over anything it's not supposed to run into. So that's a very simple agent. That's a reflex agent. At a higher level, there's a path planning agent. This knows where the robot is supposed to be going long term. It has access to a map. It plans a route. It interacts with the robot motion in order to determine if the robot is actually executing the plan. And it will replan if it discovers that the robot is not where it thinks it is. Up at the top level, there's another component of the system, which is a localizer. This is keeping track of where the robot is in the world. So again, it knows about the map, it's in communication with the odometry, it's in communication with the path planning so that it knows where the robot is supposed to be going, and it puts all those pieces together to try to identify if the robot is where it thinks it is, and it corrects the system if it determines that the robot is not where it thinks it is. So it can update the odometry, it can inform the path planner that it needs to replan because the robot is somewhere else, and so forth. So this is a complex system. It's got at least 3 layers of agents that are all working for the simple task of getting a robot to navigate around the halls of our building. All right, so all of this is just a preview of where we're going to be going. So we're going to start with these really simple agents, but there's this whole universe of complexity that we can build toward and that we need to have in order to tackle more complex tasks. So there's still a wide spectrum of different agents. We'll start with simple and build from there. All right, I'm going to pause for now, and I will see you very soon.